All right, in this video, I'd like to talk to you about resonance structures. And in order to talk about resonance structures, we're first going to draw the Lewis structure of the ozone molecule, which is O3. Now, the first thing I'll do is determine the total number of valence electrons in ozone. With oxygen, we have 3 of them and 6 valence electrons apiece. That's a total of 18 valence electrons that we're going to put in the ozone molecule. I'll draw my central oxygen. I'll draw terminal bonds to the other 2 oxygens. And now I'm going to satisfy the terminal oxygens with a stable octet. So I've got 2, I better add 6. That'll be 3 lone pairs. 1, 2, 3, 4, 5, 6, 7, 8. We'll do the same over here. So it's like I've got 8 and 8. That's 16 valence electrons used of the 18. That means there's 2 left over. And the 2 that are left over are going to go on this central oxygen. So I've used up all of my valence electrons now. Let's see if the oxygens are satisfied. This one over here feels like it has 8. This one over here feels like it has 8. But this one in the center, that only has 6. 1, 2, 3, 4, 5, 6. So I'm going to move this lone pair of electrons into a bond pair. And if we do that, our Lewis structure is going to look as follows. A double bond between this oxygen and this one. And I'll just put 2 lone pairs on this oxygen because this lone pair has been moved into a bond pair with the central oxygen. Now if we look at this particular Lewis structure, we might guess that one of the bonds in ozone is a single bond, whereas the other bond in the ozone molecule is a double bond. But this sort of violates this idea that we've been describing where it's impossible to tell the difference between this oxygen atom and this oxygen atom. I mean, after all, it's just 2 oxygen atoms on the outside that are identical, connected to a central oxygen atom. And so you really aren't going to be able to tell the difference between these 2. And so I could have just as easily drawn this. I could have easily said, you know, I'm going to move these 2 electrons into the bond with the central oxygen, and if I would have done that, I could have drawn this particular Lewis structure like this. And this is a good Lewis structure, and this is a good Lewis structure. Well, resonance is the idea that in a sense, in order to get a really good description of how the ozone molecule looks like in terms of the valence electrons, we need to think of it as both of these Lewis structures at the same time. And when we do that, we call both structures, we call them resonance structures. And we identify resonance structures by drawing a double-ended arrow between the 2 resonance structures that we've drawn. Sometimes you have to draw more than 2 resonance structures. In this particular case, we can get away with just drawing 2 resonance structures. And really, we want to think about both of these, in a sense, being the way the molecule exists at the same time. So we call this resonance structure 1 and resonance structure 2, but really, what we want to do is think of the actual structure of the ozone to be a mixture of these 2. We call it a resonance hybrid. And the way I'll represent that is what we'll do is we'll do an oxygen atom over here, an oxygen atom in the center, and an oxygen atom over here. We notice in both Lewis structures, that the outer oxygens have at least 2 lone pairs. And of course, both oxygens are bonded to the central atom like this. The next thing we do is we take the double bond and we kind of smear it out over the 2. So I'm just drawing a dotted line here. And that dotted line sort of indicates that this double bond is sort of smeared out over both bonds at the same time. And we can see this if we were to sort of calculate the bond order, the O-O bond order in this particular molecule. Well, the bond order, what that is going to be is 1 assigned here for a single bond, plus 2 assigned here for a double bond, divided by 2 connections. That's 3/2, or 1.5. So this is sort of indicating that the bond that connects the central oxygen with an outer oxygen is like a 1.5 bond. It's not a double bond. It's not a single bond. It's in between. The other thing that we have to note is on this particular resonance structure, there's 2 electrons on this oxygen, whereas in this resonance structure, the 2 electrons in the lone pair are on this oxygen. And we can kind of indicate this idea by just drawing that dashed line like this on both oxygen atoms. So this is kind of a way that I think about both resonance structures. So this would be both resonance structures. I sort of think of them in my head at the same time. And we would call the one that's in the rectangle a resonance hybrid. So you can either try to think of the appropriate Lewis structure for ozone as a resonance hybrid, such as is here, or you can think about it as existing at the same time as both of these resonance structures simultaneously. You don't want to think of this as the double bond flipping to this side and back to this side in an instant. It is as if this double bond gets smeared out between both molecules all the time, and this lone pair is actually smeared out over both these oxygens at the same time as well. Let's show how we can draw resonance structures for, say, the phosphate ion. I'll take it all the way through this. The phosphate ion, PO43-. So our central atom in phosphate is going to be phosphorus. And we'll find out how many valence electrons we should stick in phosphorus. That's going to be 1, 2, 3, 4, 5. So let's see, I've got a phosphorus. That's going to be 5, and there's one of them. That's going to be 5 valence electrons from phosphorus. Oxygen, we're pretty used to that being 6 valence electrons. Of course, there's 4 of them. That's going to be 24. 6 times 4 is 24. And then we have electrons to include. Each electron supplies a charge of 1 electron, and there's 3 of them because of the -3 charge. So that's going to be a total of 3 electrons for the -3 charge. What's that? 29, 30, that's 32 valence electrons. All right, so I'm going to draw my central atom, which is a phosphorus. I'm going to draw single bonds to my terminal atoms like this. All right, and now I'll satisfy my terminal atoms with a stable octet. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. And 2, 3, 4, 5, 6, 7, 8. 8, 8, 8, 8. That's 32. We've used them all up. And all atoms are satisfied. You'll notice we have a phosphorus with a single bond, and there's 4 of them, so that's going to be 2, 4, 6, 8 for the phosphorus, and all oxygens have 8 valence electrons. And we could stop here and say this is a good resonance structure, but we're going to apply the electroneutrality principle here and see that we can actually draw a better Lewis structure. So we're going to start with phosphorus. We're going to find its formal charge. Remember, the formal charge is 5 valence electrons. We take the valence electrons. We subtract the total lone pair electrons. There's no lone pair electrons around this phosphorus. And then we subtract half of the bond pair electrons, which is 2, 4, 6, 8. So 5 minus half of 8, that's 5 minus 4. That's a +1 on the phosphorus. So my phosphorus has a formal charge of +1. All of the oxygens here are the same. That's good. And we'll calculate the formal charge on this oxygen. And when we do that, we're going to get the same formal charge for all the others because we all have 3 lone pairs and 1 bond pair. So we'll take our oxygen, it's got a 6 valence electrons. We're going to subtract 6 lone pair electrons, and then we're going to subtract half of 2 for this bond pair here. Half of 2 is 1, 6 minus 1, that's -1. So all the oxygens have a formal charge of -1. And what's nice about this is if you add up the formal charges on all of the atoms, +1 for phosphorus, -1 for the the 4 oxygens, that cancels that, we get a -3. The sum of the formal charges should always equal the sum on the molecule or the ion. And we've done that. And that gives us confidence that this was done correctly. But I want you to notice something. If I take one of these oxygens, let's just take this one right here, and I take this lone pair, and I move it into a bond pair with the phosphorus, watch what happens to the formal charges. Let me just draw the new resonance structure that would result. Okay, this is the one where I took the lone pair, and moved it into a bond pair, so that's going to be a double bond here. And then we're going to have this here, like this. Like that. Now these oxygens are all still going to have a -1 formal charge. They're just like these oxygens here. You know, they have a single bond and 3 lone pairs. And you see an oxygen with a single bond and 3 lone pairs, that gets a formal charge of -1. So all 3 of these oxygens will have a formal charge of -1. But watch what happens to the phosphorus. In this case, phosphorus has 5 valence electrons, just like before. It has no lone pairs around it, but we're going to take half of its bond pair electrons, which now is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Half of 10, that's 5. That gives me a formal charge of 0. And now some of you may be saying, hey, wait, that exceeds the octet rule. This phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 valence electrons. Why is it doing that? Well, when the atoms get big enough, there's 2 ways you can think about this. When the atoms get big enough, that means they're in this 3rd shell or higher. You can either think of it as the atoms are large enough that it's easier for more electrons to surround it. You can also think of it as atoms that open up that 3rd shell and higher, they open up these 3D orbitals, and so they can accept electrons into the 3D. Either way of thinking about it's fine. And that's what happens here. So this is a violation of the octet rule, which I told you would happen sometimes. So this phosphorus now has a formal charge of 0, and that's better according to the electroneutrality principle, which tells us that we want to keep the formal charges as close to 0 as possible. And also, look what happens to this oxygen that's doubly bonded. If I look at that oxygen that's doubly bonded, it's got 6 valence electrons minus 4 lone pair electrons, 2 on the top, 2 on the bottom, minus half of 4 electrons, of course, in a double bond, 2 per connection. So that's going to be half of 4. Half of 4 is 6. 6 minus 4 minus 2, that's also 0. So by putting this double bond between this phosphorus and this oxygen, I've lowered the formal charge from phosphorus from a +1 to 0, and I've changed the formal charge from this oxygen from a -1 to 0. So this resonance structure is actually better than this one, according to the electroneutrality principle. So if you look, I've got a phosphorus that's singly bonded to 3 oxygens, but doubly bonded to this oxygen. So let me go ahead and draw this Lewis structure on the next page. So it looks like this. Oxygen, single bond to phosphorus, oxygen, single bond to phosphorus, oxygen, double bond to phosphorus, and oxygen, single bond to phosphorus. We'll put in the lone pairs of electrons, like that. And once again, we notice that we can draw resonance structures for this thing. In other words, all of these oxygens are identical. They all should be identical. And so really, this double bond could be represented here, it could be represented here, or it could be represented here. So I'm going to draw this double-ended arrow to indicate the resonance structure. Here I'll put the double bond up top, and all these is single bonded, like that. But instead of the double bond being here, it could also be here. So let's draw that resonance structure. So let's see, in this case it's going to be over here. I'll put in all the other lone pairs. And there's one more we can make, right? We've placed a double bond here. We've placed a double bond up top. We've placed a double bond here. And we can also put it straight down. So let's do that. The double bond straight down in this case. We'll give that one 2 lone pairs, and all the others get single bonds. And 3 lone pairs. And all of these are resonance structures of each other. So I'm going to draw double arrows between each, showing that we really ought to think of phosphorus as all of these resonance structures at the same time. So there's a sum of 4 resonance structures. And we may even throw this one in as well. We could call this one a resonance structure too. It's just not as good, according to the electroneutrality principle, as the other 4 that have drawn. But nevertheless, we can think of this as being part of it as well. Now, if I want to draw this as a resonance hybrid, well, in that case, what I'll do is I'll try to draw this double bond smeared out over all 4 phosphorus atoms. And I'll also make it where all of these lone pairs, you see this in this resonance structure, there's not a lone pair here, but in this resonance structure there is, in this resonance structure there is, in this resonance structure there is. So to sort of draw this as a resonance hybrid, I'll draw my central phosphorus. Of course, I'll draw single bonds to all the oxygens. And all oxygens, of course, have at least 2 lone pairs. All resonance structures do. And then I need to take these 3 lone pairs here, and we're going to have to kind of smear them out over the, I'll make it like this because it looks a little bit too much like a lone pair if I do too little. Okay, like that. And then we're going to just kind of dot in this double bond and smear that out over all 4 all 4 phosphorus oxygen bonds at the same time. Then we can calculate the bond order in this particular, it's the phosphate ion. So what we do is we're going to assign the value of 2 here for the double bond, 1 here for the single bond, 1 here for the single bond, and 1 here for the single bond. And we're going to divide that by the 4 phosphorus oxygen connections. That's 5 over 4, which is 1 1/4, which is 1.25. So we'd say the phosphorus oxygen bond in phosphate has a bond order of about 1 1/4. So it's a little closer to a single bond than a double bond, but it's a little bit of a stronger bond than a single bond would indicate.